Yesterday we did a little demonstration with standing waves, and we defined a standing wave in that process. We defined it as a wave that appears to be standing still. It's not really standing still. There's waves that are traveling from one end, reflecting off of another end, coming back and interfering with the first wave that's still going down. It's really an interference pattern of moving waves, but it's a wave that appears to be standing still. Now, this only occurs, these standing waves, as we saw yesterday in the demonstration, only occur with specific frequencies. Do you guys remember what those specific frequencies are? They correspond to, it's an R word, the resonant frequencies or the natural frequencies of the string. We know from our, early on in this unit, we talked about the phenomenon of resonance, where everything has a natural frequency or a resonant frequency at which it wants to vibrate, including strings. Now, when these strings are vibrating at that frequency, the waves go down at that frequency, reflect, still at the same frequency, interfere to produce this pattern, this interference pattern that appears to be standing still. It happens only at those frequencies. You saw yesterday in the demonstration, if we go above that frequency or below that natural frequency, yesterday I think it was 5 hertz, right? 5, 10, 15, 20. If we go above or below those natural or resonant frequencies, then we get not a random interference pattern, but it's certainly not a standing wave, right? It looks almost like a random interference pattern. We match those natural frequencies, though, we get this standing wave that appears something like this. It's not a great diagram, actually, but more or less shows us what we want here. We've got a wave like this, and then we've got the corresponding wave like this. Now, yesterday we saw that when we took a video of it, actually, some of us were able to see on that video that, and when we slowed down that video, that this string that was producing this big fat spot was actually going up and down. And of course it is. We can't have the string in two places at the same time. The string is either here, or it's here, or it's somewhere in between. It looks like it's everywhere at once. It looks like the wave is standing still. But of course that wave or that string has to be in one place or the other or somewhere in between. Again, when we slowed that down in slow-mo video yesterday, some of us that saw that video were able to see that in fact the string is in one particular place at one particular time. This bump that appears to be everywhere at the same time is what we call an antinode. That's a result of constructive interference. Right? It's constructive interference. We're taking a wave, we're taking another wave that's on the same side of the equilibrium position, and we're adding them up to produce constructive interference. We got another antinode over here, another antinode over here, and another antinode over here. But in between those antinodes, we have what's called nodes. Nodes are where we have destructive interference. This is where we have, because of the particular frequency that we have this wave traveling at, this is where we have a crest always meeting a trough, always completely destructively interfering with each other, producing a spot that doesn't actually move. So this wave moves up and down between the two spots. This spot of the wave doesn't, because it's always destructive interference. Same deal here, same deal here, same deal here. So in this particular standing wave, we have 5 nodes and we have 4 antinodes. If we jack up the frequency a little bit, as we saw in the demonstration yesterday, then we could produce 5 antinodes and 6 nodes, or 6 antinodes and 7 nodes, and so on and so on and so on. So how exactly do we figure out what frequency this will occur at? How exactly do we figure out what frequency this 4 antinodes, or the 5 antinodes, or the 6 antinodes, or whatever the case may be, will occur at? We're going to draw some pictures here. The first picture is the first thing that we saw in our demonstration yesterday. This is when we have the first standing wave that occurs. It's one antinode and two nodes. The second one that occurs, the second standing wave that occurs, is when we have two antinodes and three nodes. The next one that occurs is when we have, you can probably guess here, three antinodes and four nodes. And so on and so on and so on. First three are probably good enough. We're going to define the length of the string in all three cases as L. So from one end of the string to the other is going to be called L. Whether we're dealing with one antinode or three antinodes or 15 antinodes, the length of the string is going to be L. And it's not changing, right? If we have one antinode, as we saw yesterday, or what did we go up to yesterday? I think we went up to 12 antinodes. The length of the string didn't change, right? The length of the string was, I don't know, 2 meters, let's say. It was the same for the first one as it was for the 12th one. We're going to call it, in general, L. Then what we're going to do is define the length of this string in terms of the wavelength. So we're going to say here that, let's draw out a wave actually, and then we'll do that. We're going to say that this length is equal to 1/2 lambda. You see why I'm doing that, guys? Let's trace this out here. That's one crest, right? That's one crest. That's a half of a wave. So we're going to say the length of this, because it's only one crest, is 1/2 of a wave, or 1/2 of lambda. For the next one, what do we got for the next one? Well, we're going from here up through a crest and then down through a trough like this to here. So that's going to be, what's that going to be? Lambda is equal to L, right? Lambda is equal to the whole wavelength there. Anybody want to take a stab at the next one? How many waves we got for the third one there? Good, 1.5 waves. We're actually going to call it 3/2, although you really could, whoops. You actually could call it 1.5 or 1 1/2, doesn't really matter. Just that we're going to start seeing a pattern in a moment here, and it's a little bit easier to see that pattern if you've got it listed as an improper fraction there, 3/2. All right, now let's rearrange each of these to solve for lambda. So if L is equal to 1/2 lambda, then lambda is equal to 2L. Lambda, we already solved for lambda there, it's L. Here we'd say lambda is equal to 2/3 times L. 2 goes up, 3 goes down, right? So we've done the setup work. Okay, we've done the setup work. The next step is actually determining what frequency this will occur at. Okay, yesterday, we measured the frequency of the first one to be 5 hertz, the frequency of the second one to be 10, the frequency of the third one to be 15. Today, we're going to predict what frequency that will occur at, calculate what frequency that will occur at. We know that the universal wave equation says V is equal to F times lambda. So let's rearrange that to solve for F. It's V over lambda. Now watch very carefully. If F is V over lambda and lambda is 2L, then F would be equal to V over 2L. So what frequency would the first standing wave occur at? It would occur at the speed of the wave, whatever the speed of the wave is, divided by 2 times the length of the string. The second one would occur at, well, V over lambda again, but what's lambda? It's L. So we're going to say V over L. The third one would occur at, well, V over lambda, V over, what, 2/3 L? That works, but we can simplify that a little bit. V over 2/3 L is exactly the same thing as saying 3/2 times V over L. Yeah, notice? You don't understand why lambda keeps getting smaller? Okay, good question here. The length of the string is the same, right? Regardless of whether we're dealing with the first standing wave or the second or the third or the 14th standing wave, the length of the string is the same. But if you get more of a wave in that length of the string, and that's what's happening here, right? Here we've got a half of a wave, just one crest. Here we've got a full wave, a crest and a trough. Here we've got 1.5 because we've got 2 crests and a trough, right? Does that make sense so far? If we've got more of a wave in the same length, then the length of the wave has to be shorter. Does that make sense? Okay, it's like, this is a silly analogy, but just coming up with it on the fly. But let's say the length of this room is, let's say, 8 meters. Okay, from front to back, it's 8 meters, and we lay people down head to toe. Okay, head to toe from front to the back of the room, and it takes, and we got I don't know, 6 people. It takes to go from the front of the room to the back of the room, right? If we want to have more people laying down, then the people have to be, no. The people would have to be smaller, right? The people would have to be shorter. So if we want to have more waves in the same length, then we have to have a shorter wavelength. So that's why the wavelength ends up getting smaller. Okay, good question. Okay. Seriously, guys, that's the kind of question. We don't want to just memorize this stuff. We want to understand this stuff, and that's the kind of question that helps us to understand this stuff. All right, what I want you to see right now is the pattern that's formed here. The first standing wave that's formed here is V over 2L. We're going to call that, by the way, the first harmonic. The second standing wave that's produced here is V over L. If we write that a little bit differently, we could say F is equal to 2V over 2L, right? 2V over 2L is exactly the same thing as saying V over 2L, right? So V over 2L, 2V over 2L, that means the second one that we see is twice the value of the first one. We're going to call that the second harmonic. And I'm going to make a little note here that the second harmonic is 2 times the value of the first harmonic. And the next one that we see here, what do we got? V over 3 over 2 V over L. We had V over 2L. We had 2V over 2L. We have 3V over 2L. It's going to be 3 times the value of the first one, right? We're going to call that the third harmonic. And it keeps going up from there, right? The fourth harmonic would be 4V over 2L. The fifth harmonic would be 5V over 2L. The 16th harmonic would be 16V over 2L. And its value would be 16 times the fundamental frequency of the first harmonic. When you pluck a guitar string, there's 1,000 or more different frequencies produced in that guitar string. But most of those frequencies die out right away, disappear right away. The ones that remain correspond to the resonant frequencies of that string. They correspond to the standing waves produced in that string. Does that make some sense? The frequency that you hear ends up being the frequency of the standing wave, the resonant frequency of that string. Now, who plays guitar here? Okay, you got asked that question the other day, right? Those of you that play guitar, everybody knows this, but especially those of you that play the guitar, there's 2 ways to change the pitch of a string when you pluck that string, right? What's one of the ways that you can change the sound produced when you pluck one string? You tune it, right? And how do you tune it? That little tuning knob or tuning dial or whatever it is at the end? Yeah. Okay, yeah. Yeah, that's right. But let's look at that little tuning knob or whatever you call it. We'll call it the tuning knob that you have at the end, right? What do you do when you turn that? You're not changing the length of the string, right? What are you doing? You're tightening the string or you're loosening the guitar string, right? What do you do when you tighten the string or you loosen the string? You change the speed. When you tighten it, the speed of the wave increases. right? The sound wave in that string goes faster in a tight string than it does in a loose string. So when you tighten that string, the speed goes up. What happens to the frequency? It goes, as V goes up, F goes up. That's why you hear a higher pitch when you tighten the string, right? What's the other way of changing the pitch of the string? Put your finger on a fret, right? When you put your finger on a fret, what happens to the pitch that you hear? It goes higher, right? Why does it go higher? You're not changing the speed of the sound in the string. Why does it go higher? Because when you put your finger on a fret, you're shortening the string. As L goes down, F goes up because they're inversely related to each other. So the way to get a different standing wave produced in a guitar string is to tighten or loosen the string, or to change the length of the string by putting a finger on a fret. That's how you get a different sound, right? There's an art behind music, but there's also a science behind music. Let's take a look at an example here. It says a 25 centimeter long string is set in vibration. The speed of the wave through the string is 500 meters per second. What are the first three possibilities for harmonics in the string? Now you got a couple of options here, guys. You can derive the equation, which honestly I'd like you to do because I think it's useful to go through that process of deriving the equation. But in the end, there's also a simple equation that you can memorize. We'll derive it. L is equal to 1/2 of a wavelength there, because it's just a crest, right? Half of a wave. So does that make sense? Let's rearrange that to solve for lambda. It becomes 2 times L. And then F is equal to V over lambda, but F becomes equal to V over 2 times L. There's my equation. The first harmonic for a standing wave in a string that's attached at both ends is always going to be V over 2L. Now we know the speed of this. It's 500 divided by 2 times the length of the string, 0.25 meters. Always got to be in meters here, right? 500 divided by 0.5 ends up giving me 1,000 hertz. Or we'd say 1.0 times 10 to the 3 hertz. So you can memorize this equation, or you can derive the equation, which I would suggest you do, because when we go on to our next step of standing waves in air columns, like woodwind musical instruments or brass instruments, the equations are a little bit different. What a lot of people end up doing is confusing the two if they memorize them. If they derive them, less source of confusion. There's the first one. There's the first harmonic that's produced. Now, we got a couple of options for finding the second harmonic. We could derive the equation for the second harmonic. What's the easier way, though? Nothing that we really have to memorize. What's the easier way? Yeah. Just double it, right? Derive the equation, or get the first harmonic like we just did, and then just multiply it by 2. We're going to say F2 is equal to 2 times 1,000. And of course, the third harmonic, F3, is 3 times 1,000, 3 times the fundamental. So if you do memorize the equation, as opposed to deriving it like I'm suggesting, please don't, whatever you do, don't memorize all of them. Memorize the first one, F is equal to V over 2L, and then just remember that the second is twice the first, and the third is 3 times the first, and so on. All right? All right, let's have a look at question number 5 on that worksheet. It says the length of a particular vibrating spring is 1 meter. It says the speed of the wave in the string is 1,000 meters per second. We want to determine the wavelength of the first harmonic, and we want to determine the frequencies of the first 3 harmonics. So F1, F2, and F3. Goodness, we've got 2 givens, and we've got 4 unknowns that we want to find here. So how do we go about doing this? So let's do one thing at a time. We know the equation for the first harmonic is this. F is equal to V over 2L. You can remember that equation or you can derive that equation. Either way, you're going to end up with F over 2L for the first harmonic. Let's calculate the value of that first harmonic now. V is 1,000 meters per second. The length is 1.00 meters. So we're going to say 1,000 divided by 2 meters ends up giving me a frequency for the first harmonic of 500 hertz. Okay, there's F1. Well, we can find F2 and F3 pretty easily, right? F2, the second harmonic, is going to be 1,000 hertz, or 1.00 times 10 to the 3 hertz. And F3, the third harmonic, will be 1.50 times 10 to the 3. It's 3 times the value of the first harmonic. Good? Now, how do we find the wavelength of the first harmonic? If the frequency of the first harmonic is 500 hertz, and the speed of the wave is 1,000 meters per second, then we can pretty easily find the wavelength of the first harmonic. We're simply going to say V over F1 there, 1,000 meters per second, which we were given in the question, divided by the frequency of the first harmonic, which we just calculated a second ago, gives me 2.00 meters. Yes, I was going to say there is a shortcut to do that as well, but if you use the shortcut, it requires you to remember something else or to derive the equation, as opposed to just going at it the way we did here. Okay, if you remember the equation, what you did is not the easiest way. If you're deriving it, then what you did is the easiest way. Hey, if you didn't hear what he said, guys, he said, couldn't you just say lambda is equal to 2 times L? Well, let's go back. Let's go back for a second and derive that equation. The first harmonic, we said L is equal to 1/2 lambda. So lambda was equal to 2 times L. So if you're deriving the equation, again, all you got to do is say lambda is equal to 2 times the length of the string, 1 meter, and we're good to go there. That's a shorter way, right? That's a shorter way, but it requires you to derive the equation as opposed to memorize this. Whatever works for you guys. Guys, you notice how I only used that one equation? We were dealing with the second harmonic, the third harmonic, but we only used the equation for the first harmonic. That's what we're always going to do. We have all these equations for the second harmonic, for the third harmonic, and so on. The only reason I derived those to show you those, the only reason I did that was to show you that the second was twice the value of the first, and the third is 3 times the value of the first. Okay, we don't need to remember those equations or even use those equations. Always deal with the first harmonic, even if you're not looking for it. Okay, even if the question said, what's the frequency of the third harmonic, and you weren't asked for the first harmonic. Get the first harmonic, and then multiply it by 3. That make sense? All right. You guys keep going on that worksheet for another few minutes, and then we'll do one more little thing with it. Let's take a look at number 9 now in the worksheet. Everybody just have a look up here. It says the frequency of the fifth harmonic of a particular vibrating spring is 1,000 hertz. The frequency of the fifth harmonic is 1,000 hertz. So let's write that down. F5, the frequency of the fifth harmonic, is 1,000 hertz. If the length of the string is 65 centimeters, determine the value of the speed of the wave in the string. All right. Okay. Let's just take a step back from this. What do we know? We know the equation for the frequency of the first harmonic. It's V over 2L. Well, we could derive the equation for the frequency of the fifth harmonic as well, but it's not necessary. If we have the frequency of the fifth harmonic, why not get the frequency of the first harmonic and then use the equation for the first harmonic, the first standing wave that's set up in the guitar string when you pluck it? If F5 is 1,000 hertz, then F1 will be 1,000 hertz divided by 5. So we're going to say F1 is going to be 200 hertz. Now, we can rearrange this to solve for V. It becomes F times 2 times L. Right? The 2L goes up by multiplying. The frequency is 200 hertz times 2 times the length of the string in meters, 0.65 meters, gives me an answer for number 9 of 260 meters per second. I'm sorry? No, 6.5 centimeters would be 0.065. 65 divided by 100, right, gives me 0.65. So we're dealing with a fifth harmonic here, solving for a speed of a wave when we've got the value of the fifth harmonic. That's okay. Get the first. Remember what I said when we started this stuff. Use the equation for the first harmonic. Whether you derive it, whether you remember it, doesn't really matter. Get the equation for the first harmonic. If you don't have the value of the first, then get the first and use that equation and get what you need to get. Right? Okay, we're going to move forward a little bit on this here. Not going to talk about standing waves produced in strings. Now we're going to talk about standing waves produced in instruments that use air as opposed to, say, steel strings like guitars or strings like we saw yesterday in our demonstration. We blow across the top of a water bottle like we did yesterday in another demonstration. We hear that sound produced, right? We blow into a tuba and we hear a certain sound produced. How do we analyze the sound that's produced in those? Well, it's almost the same. But understand, when you have an instrument or some kind of source of sound that is not a string and that is not attached at both ends, but rather, let's say an instrument that's open at both ends like this, the standing wave that's produced looks a little bit different. Instead of getting, like what we had, a node at both ends, we end up getting an antinode at both ends with a node in the middle. That's the first one. The second one that would occur, this has two bumps or two antinodes. The second one would have three antinodes or two nodes. The third one would have four antinodes or three nodes. We go through the same process of deriving an equation for the first harmonic and so on. This one, we're going to say L is equal to, well, that's a half a wave, right? We're going from top of a crest to the bottom of a trough. That's a half a wave. This is going to be a full wave. This is going to be, what do we got here? Let's trace it through. This is one complete wave, and then another half. Aren't those the exact same thing as we had for the strings? Half a wavelength, and three halves of a wavelength. We're going to say F is equal to V over lambda, or F is equal to V over 2L. It's exactly the same equation we had for the strings. V over lambda or V over L. Exactly the same equation we had for the strings. V over lambda or is that right? That's not right. Or it should be not 2/3, but it should be 3 over 2, right? 3 over 2, V over L. Again, the exact same equation for the third one that we had for the strings. Bottom line is, although the equations are the same, the sounds ends up being different. This is the first harmonic, right? Second harmonic. The third harmonic. Second is 3 times the value of the first. The third, 2 times the value of the first. The third is 3 times the value of the first. The sounds ends up being different, though. Can anybody tell me why? If I pluck a guitar string that happens to be 3/4 of a meter long, I blow into a musical instrument with 2 open ends that happens to be 3/4 of a meter long. Why is the sound produced differently, even though the equation is the same? Good. The speed of the wave is different. The wave travels at a different speed in a guitar string than it travels through air in an instrument that has 2 open ends. Does that make sense? So if you want to produce the same note in the instrument that produces sound through air with 2 open ends, you've got to have a different length to correspond to compensate, I should say, for the different speed. The equations are the same. We deal with it in exactly the same way, but the numbers will be different. When you're solving problems involving this, though, it goes exactly the same way, right? Always deal with the first harmonic. If you want the third harmonic, that's fine. Get the first harmonic, multiply it by 3. If you have the value of the fifth harmonic, get the first harmonic, and then plug it into the equation for that first harmonic. Yes, good point. That should be 2L as opposed to V over L. Sorry, V over 2. It should be V over 2L for sure. Same equation as it was for the strings, right? All right, last one here. This is probably a more realistic musical instrument where we have air producing the sound. We don't usually have too many musical instruments where both ends are open. Usually you have one end that's open and one end that's closed. When I blew across the top of the water bottle yesterday to produce the sound, we had one end that was open, that was the top of the water bottle, and one end that was closed. That was the bottom of the water bottle, or at least the level where the water was, right? One end open, one end closed. That's what we're dealing with right now. One end open, one end closed. We know from our analysis of strings that when we have a closed end or a fixed end, we have to have a node. But we know that from our analysis of air columns, where we had two open ends, we know that we have to have an antinode at the open end. So our first harmonic here is going to look like this. It's going to have a node at the fixed end or the closed end and an antinode at the open end. Now, you can't physically see this inside the instrument, right? Because it's air vibrating back and forth. But if you could see it, like we did in the demonstration yesterday, this is what it would look like. We couldn't see this exact one in the demonstration yesterday because it was involving a string, right? And the string was fixed at both ends. It had to have a node at both ends. But when we have an air column, again, if it's closed at one end, open at the other end, it's got to have a node at one end and an antinode at the other end. If it's open at both ends, it's got to have an antinode at both ends. Okay, next one. First one has one antinode. The next one's going to have two antinodes. It's the next possibility that's produced here when we have to meet that criteria of having a node at the closed end and an antinode at the open end. Okay, one bump or one antinode, two bumps or two antinodes. And the next one you could probably predict is going to have three bumps or three antinodes. You're going to say the length of the string, not really a string here, I guess, right? Length of the air column, length of the musical instrument is going to be L. This one's a little bit tougher in deriving. Okay, this is the waveform. The first one is how much of a wave. Anybody want to take a stab at that? How much of a wave do we have there in the first one? Stop me when I've reached the peak there, okay? Stop. How much of a wave is that? No, it's not a half. This would be a half, right? It's a quarter, yeah. So we're going to say L is 1/4 lambda here. It's a little bit different than the last two that we saw, right? For the open air column where it was open at both ends, it was 1/2 lambda. For the ones where we had the string attached at both ends, it was 1/2 lambda again. This time it's 1/4 lambda. Next one is what? 3/4, yeah. We're going from here all the way down to here. That's going to be 3/4 lambda. So L is going to be equal to 3/4 lambda. And then the next one, that's one complete lambda, right? But we're going back up to here. So it's going to be 1 and 1 1/4. Yeah, 1 1/4. Let's just say it's 5/4. Okay, L is equal to 5/4 lambda. Makes sense why those numbers are as they are? All right, let's rearrange them. Solve for lambda. If L is equal to 1/4 lambda, then lambda is 4L. 3/4 lambda, then lambda would be 4/3 L, right? 4 goes up, 3 goes down. 5/4 lambda, then lambda would be equal to 4/5 L. We know that F is equal to V over lambda. That's our wave equation. Let's sub in 4L for lambda here. Oh, you remember what we had before? F was equal to V over 2L for both the string that was attached at both ends and the air column that was open at both ends, V over 2L. Now we've got V over 4L for an air column that's open at one end and closed at the other end. Remember what I said a few minutes ago? You can memorize that first harmonic, but it starts getting a little bit confusing. It does here because now we've got two different values, two different equations for the first harmonic. V over 2L, V over 4L, depending upon what situation you're in. What about this one? V over lambda. All right, V over lambda. Let's sub in 4/3 L for lambda. It becomes V over 4/3 L. If we rearrange that to simplify it a little bit, we're going to get F is equal to 3V over 4L. Right, flip the 4 over 3 over. 4 over 3 over. Same deal here. V over lambda. Let's sub in 4/5 L for lambda. If we simplify that a little bit, it becomes F is equal to 5V over 4L. Completely different equations than we got for the two open-ended air column and the string that was attached at both ends. We're going to still call this one the first harmonic because it's the first standing wave that's produced here. But the next one, look at it closely. Look at the equation. V over 4L, 3V over 4L. How much bigger is it than the first one? 3 times. We're going to call this the third harmonic. There is no second harmonic. When you pluck a guitar string, you can get a first, a second, a third, a fourth harmonic. When you blow into a clarinet, you can only get a first harmonic or a third harmonic or a fifth harmonic and so on. You can't get the second harmonic. Next one is going to be the fifth harmonic. So we analyze these questions involving open-ended air columns, both ends open, exactly the same way as we did strings. We analyze these ones involving one open end, one closed end in almost the same way. We got to be careful that A, for these ones we use a different equation, V over 4L instead of V over 2L, and we remember B that we don't have even numbered harmonics. So if a question says, what are the values of the first 3 harmonics that you hear? You calculate the value of the first one, it's 200 hertz. What would the second one be that you hear? 600 hertz, because it's 3 times the value of the first one. And what would the third one be? It would be the fifth harmonic, right? You don't get a second and fourth. So the second one that you hear would be the third, and the third one that you would hear would be the fifth. So otherwise, exactly the same. Just remember the equation is different, and just remember that F3 is equal to 3F1, and F5 is equal to 5F1. There is no 4F1s or 2F1s. All right, here's one more example, last one. A little bit of a typo in this. It says, what are the frequency of the first 2 harmonics observed in a 40 centimeter long air column? Well, we have to know what kind of air column it is, open or closed. We're going to say that this is a closed air column. A closed air column means it's one end open and one end closed. That's the last example we just did, right? An open air column is when both ends are open. So whenever you see the term closed air column, it's this one. Whenever you hear the term open air column, it's this one. We're dealing with a closed air column in this question, so it's the V over 4L, the 3V over 4L, the first, the third, the fifth harmonic. The other thing you got to recognize is that when we have a temperature given to us, we can find the speed of sound in air. The speed of sound in air, you're going to have to write this one down. It's on your data sheet, but write it down anyways. The speed of sound in air, this doesn't work in a string or in steel or anything else, but the speed of sound in air is 331 meters per second plus 0.6 times the temperature in degrees Celsius. So we're going to say in this case 331 meters per second plus 0.6 times 30 degrees Celsius. 49. This works out to be 349 meters per second. Yeah, that works nicely if the sound is in air. Doesn't work at all if the sound is in a string. All right, what are the frequencies of the first 2 harmonics? We've got the length of this air column. It's 40.0 centimeters. We've got the speed now. It's 349 meters per second. We want to find F1, and we want to find, tell me the other thing we want to find. F3, good. The third harmonic is the second one that we would hear. So we're going to say F1 is equal to V over 4L. We can derive that equation, or we can remember that equation. If you remember it, though, be careful to keep them, the two of them straight. V over 2L, V over 4L. 349 meters per second here, divided by 4 times 0.40 meters. We end up getting a frequency of 218.125 hertz. We're going to round that to we'll just say 218 to 3 digits. Now we want to find the third frequency. Sorry, the second frequency, the third harmonic. Cody, what do we do? Good. We're just going to multiply it by 3. 218.125. Use the unrounded number there, times 3. It equals 654. Is that okay? It's almost what you spent 15 minutes working on that worksheet on, right? It's almost the same thing. Two things to remember. The equation for the first harmonic is different, and you don't have the second or the fourth or the sixth or so on harmonics. Strategy is exactly the same. Deal with the first harmonic in the equation for the first, and then multiply it by whatever you got to multiply it by to get your harmonic. Okay? So your homework for tonight is the back side of that worksheet. You got about 5 minutes to work on that now in class, okay?